Swayam Prabha. Digital India. Educated India.
So, if you look into this, equality in this case is attained when G is a complete bipartite graph with equal partition, right, K n n, right, because K m n we have already seen the Laplacian spectrum of this is nothing but 0 m n and m plus n, right. M plus n is going to be maximum when both m and n are equal, right, and that would be twice the degree of max degree, right. So, this we have seen already. So, this is of order m minus n and this. Right. So, from here we can see that when m is equal to n and G is complete bipartite, then we achieve that delta 1, the max degree is twice, the maximum largest eigenvalue is twice the maximum degree. Okay. So, this is also in some sense tight bound for these classes of graphs. Okay. Okay. So, next part what I want to talk about is Laplacian spectrum of certain classes of graphs under graph operations. So, what are the graph operations that we have seen already or you have seen already? You are given two graphs, you are going to do something on that. What are all the things that you can do? Union of two graphs, can you, I mean that is a graph operation, right, union. So, we can think of G1 union G2, disjoint union, you just put them together, that is one option. You will also have G1 join G2. So, what is G1 join G2? You take the graph G1 and G2, you add to every vertex of G1, you add an edge from G, I mean to every vertex in G2, you add an edge from G1 from every vertex of G1, right. So, this is G1 join G2. Any other operation have you seen? Huh? Cartesian product, yes. So, G1 cross G2, this also we have seen the box product, right. So, what will happen to my Laplacian if I know for the basic graphs? I know Laplacian of G1, Laplacian of G2, or if you are given a graph, but you can visualize the fact that that can be written as join of two graphs or Cartesian product of two graphs, then can I reduce my problem to computing the Laplacian of the smaller graph instead of doing it for the whole graph, because obviously if I want to compute Laplacian or the determinant for a 2n vertex, that is going to be comparatively time consuming when I do it for n vertices, right. So, in that context can we give some values which from here itself, so that I know, okay, if I know the Laplacian spectrum of G1 and G2, I can immediately write for G1 join G2 or G1 product G2. So, what say suppose let us start with the G1 join G2, because this is a very nice structure, you have kind of two components and there is complete connection between them, right. So, what can we say about the Laplacian of this? So, we want to talk about spectrum of this. So, first let us look at how will my Laplacian matrix look like. Say let us have L of G1, let it be the Laplacian of G1, L of G2, let it be the Laplacian of G2, right, and let me also give you spectrum of the Laplacian of G1 is say alpha 1, alpha 2, alpha n, and spectrum of L of G2 is say beta 1 to beta m, because I am not committing anything on the number of vertices being equal. Okay. So, we will just take n and m vertices are there in both G1 and G2. So, what will be the join, and how will my Laplacian first of all look like? It should not be difficult to see. Okay, so first how much we have? So, this L of G1 join G2 is going to be a matrix of order n plus m cross n plus m, right. It is a square matrix of order n plus m cross n plus m. So, first n rows, so we will have a block. So, the first n rows will be L of G1 minus 1, everything is minus 1. So, we have a minus of J matrix, right. So, this would be an n by m matrix, right. What about this? M cross n, L of G2. So, this is his proposal. Does everybody agree to this? Diagonals change, right, because you are adding degree increases, it is no longer just L of G1. So, what will be the matrix? So, this would be plus m I n, this is an n by n identity matrix where every diagonal entry is m, and this would be plus n I m, right. So, now can we think about the Laplacian spectrum for this? Given these quantities, you know the spectrum of G1, you know spectrum of G2, we just need to look for spectrum of this join. And of course, here we also have this, right. So, this is, let me just take because we have at least one identity matrix which is 0 eigenvalue. So, let me just write this as 0. Okay. So, one is obviously clear that this is again Laplacian. So, this is going to be there is a 0 eigenvalue for this, that is clear, right. So, for the spectrum there is 0 eigenvalue. Okay, say let us look into what kind of other eigenvalues can be present, right. So, what else do you expect to be there? Okay. So, let us think of this vector, look into this. Let us look at the corresponding eigenvectors of L of G1 with respect to alpha i's, right. Say with respect to alpha I, let lambda xi be the eigenvalue, and let us also take yj to be the eigenvector of L of G2. Here I am just trying to construct, instead of doing it manually trying to expand it, we will try to see it from the eigenvectors, we will try to pull out the eigenvalue from here. Okay. So, with respect to beta j. So, let me look into this. So, is there any guess first of all, what should be my eigenvalue given these things? Given alpha i's and beta i's, can I make a guess, at least some wild guess that this can be a eigenvalue? That is why I gave you some more clue also about eigenvector. Can you use that? So, let us look at this eigenvector. The first, because xi is going to be of order n, right, it is a vector of order n, yj is going to be a vector of order m by 1, right. So, let me just look at this eigenvector to xi, let us append zeros, m zeros to the bottom. Okay. So, for this vector, can I see whether Lx is going to be equal to some lambda x? See, I am just trying to write it from whatever we have, I should not be going beyond that. So, what can we say from here? So, if I just take this x vector multiply to this Laplacian here, can I say something? So, if you do this as a block multiplication, what will happen? Say I just take this vector x and multiply it with L. So, that means what? This right side say minus j n by m vector, what will that happen with my x? Say first row and x vector, if I just take this multiply, what will I get? You have a plus mi, right? That plus m xi would be added to this, the first component of x would be added to the diagonal. So, there is going to be a plus m hanging out, right. Apart from that, this L of g, the first row of that would be contributing to my lambda into x, the first vector part, right. So, this block, so this block on the top will be just contributing to the fact that this would be alpha I plus m times x, right. What about the lower part? This side you will have n ones and there is a plus n1 will be there, so that vanishes. So, you will only have this value remaining. Okay. So, if you look at Lx for this vector xi, if I take the ith eigenvector, I will get the corresponding ith eigenvalue of g1 plus m times. Okay. So, this is going to be the eigenvalue of one of the eigenvalues. So, as I vary my I will get all possible eigenvalues here up to n minus 1. Right. Similarly, if I look at m minus 1 entry, right, that would also give me a similar expression, say Ly if I take. So, y is going to be nothing but, so let me write it here. So, let y be equal to 0 n's, the first n zeros you have, after that followed by the vector yj, the eigenvector of the L of g2, from there you pick it up. So, for this y, you can immediately see that your Ly is going to be equal to beta j plus n times y. Okay, it is just a simple exercise, you can just try to multiply and see. So, we can say that from here beta j plus n is going to be an eigenvalue, similarly alpha I plus m are going to be eigenvalues, right. So, for what I 1 less than or equal to I less than or equal to n minus 1 and 1 less than or equal to j less than or equal to m minus 1. Right. So, we have now found out, at least I know 0 I have found out already. So, now we have m minus 1 plus n minus 1 plus 1, right. We have got m plus n minus 1 eigenvalues out of this, right. One more eigenvalue we need to find, right. So, from here if I just try to do it, if we multiply this, expand it, and if we do, you can do it. I am just giving you another alternate option. Consider this vector, eigenvector, where you take, what is the first row? I have mi1, right. So, I can just write this as m times the first vector, I mean the first n1 n entries to be m and followed by n, right. So, the vector is going to look like this. So, m n times and then followed by n m times, right. So, if you look at this vector, this is also an eigenvector for which eigenvalue, the same way, same principle if you apply from the previous one, you will just get, so let me call this as my vector z. So, Lz is going to be nothing but giving you n plus m times z. Okay. So, actually this would be the vector of eigenvector for n plus m. So, n plus m is another eigenvalue for this matrix. Okay. So, I mean I am not doing it in the traditional way of computing, I am just giving you in the reverse direction. So, you can guess from whatever values you have, right. So, these are the spectral values that we get, okay, for this join matrix. So, for join you can see that the eigenvalues, it is not going to go beyond the given entries. So, we just need to be cautious here. Okay. Okay. So, this is about join. So, now can you give me an eigenvalue of join of itself, join with itself? What will it be? Just an exercise, quick exercise. Having known this value, the spectral of this L of G1 join G2. I am just asking you, what if my G1 is equal to G2? Yeah, 0 ones, 2n ones, yes, twice. So, for every alpha I, you will have, it is going to be repeated twice, right. So, this is just to, so where alpha I is nothing but the spectral value of L of G, right. Okay. Okay, another exercise. Suppose I have the graph G and I know the Laplacian of G. What can we say about the Laplacian of G complement? Yes. We will then go into the spectral values, but first how will my matrix look like? So, if I have G and its Laplacian is there, so what will be G complements Laplacian? First of all, what is G complement? If there is an edge in G, then there is an, there is no edge in G complement, right, vice versa. So, minus J n plus n I minus L. What is this J n? All ones matrix, okay. So, let us keep it this way. So, n I minus L minus J, is that okay? Yes, no? Is it right? Come on, guys. So, I think this is wrong. Can someone tell me why? So, this is the expression that he has given. So, for G complement, wherever you had 0 in L, you are going to write it as minus 1, and wherever minus 1 was there, you have to write it as G 0, right. So, for that, what should I be doing? So, diagonal entries, we will talk about this part. So, what is happening here in this expression, whatever he has given, what is happening here? You look at any ijth entry, typical ijth entry in the matrix, what will that value be? Suppose there was an edge, suppose my I is adjacent to j, right. What will be this entry, like the way he has given? I am just going with whatever he has given. So, if I was adjacent to j, my minus L would give me plus 1, right, and minus j would give me minus 1. So, what does that mean? 0. So, where is I is adjacent to j? in G complement or in G? In G, right? And that is what I am asking. So, I is adjacent to J in G. So, what about if I is not adjacent to J in G? So, 0 minus 1. So, this is also fine, right? What about the diagonals? So, you have n minus degree of j minus 1. Is that okay? Yes, no? So, why no? N plus 1 is n plus 1. So, okay, there is now a proposition of n plus 1 times I. Actually, somebody is missing something else here, because once you decide this, then your eigenvalue is going to be direct. That is why I am putting so much time here. Unless you are clear about how your matrix is going to look like, getting the eigenvalues for that would be very difficult. If you should first be clear about how your matrix is going to look like. Is it ni or n plus 1i? Okay. So, first of all, given any vertex, what is the maximum degree that is possible? N minus 1, right. So, if it is there, I mean if number of edges are there in G, then the rest is going to be in G complement, right. Total degree is n minus 1. So, there is no confusion in this part, I guess, here, right. So, any other changes? So, it is not n plus 1, it is n times I, right, because n minus degree is going to give you, I mean there is this minus 1 coming from J. So, n minus 1 minus degree will give you the degree in the graph G complement. Okay. Come on guys, you are too slow. Okay. So, now tell me what will be the spectrum. You know the representation, you know the spectral values of I, J and L. If you know that, then what will be the spectrum of G complement? Okay, I will give you, you people can think about it. So, if spectrum of G has lambda 1 to lambda n, and we know the spectrum of J also, and for identity matrix also. So, spectrum of J complement would be nothing, G complement would be nothing but n minus lambda 1, n minus lambda 2 and so on up to n minus lambda n minus 1 followed by 0, right. The first n minus 1 eigenvalues takes this form, it is just going to be n minus of the lambda I values, okay, and 0 will be another eigenvalue for this. So, you can now combine these two questions. What can we now say about a graph G? My next question is, suppose I have a graph G, okay, and I know this graph G is join of say two graphs. Okay. Suppose my G is join of some two graphs. Just by looking at it, I try to grasp the fact that it is join of two graphs. What can I say about G complement and its connectedness, connectivity part? From the eigenvalues, just by looking at the eigenvalues, can I say something? We know if you look at this graph, then I can talk about G complement structurally, right. But I do not want structural answer, but I am asking you in terms of eigenvalues, what can I say about my graph G complement? if I know that my G is join of some two graphs. Yes, at least what does your structural intuition say? Yes, we have seen these two results, both I am just showing it to you again. So, I know this, the spectral value of join of two graphs is going to be this, right, and the spectral value of complement also I know it is going to look like this. So, from these two can I conclude something about my spectral values of G complement right from here for this particular structure and say something about its structure. See, this whole exercise is for you to realize how spectral values are going to impact, right. So, what do we know? We know this is going to be spectral value of G1 join G2, right. So, if I know my given graph is join of two graphs, then what can I say about that? I know that there is an eigenvalue of size n plus m, that is for the two parts, right, join of G1 and G2. So, that is going to be total number of vertices in my graph, right. If I say join of the two parts, then it is going to be the total number of vertices here, right. If I go into the complement, we know that we are going to look at the complements. If there is a positive eigenvalue, they will all be nothing but n minus of that is going to be a eigenvalue for the complement, right. So, if I have n as an eigenvalue in G1 join G2, then n minus n would be 0, right, and I also have another 0 eigenvalue that is sitting predominantly, right. So, there are at least two 0 eigenvalues. So, what can we say about this now? My G complement is disconnected, right, because there are at least two I know. Immediately I can say from here, because there exist two 0 eigenvalues, right, or I should just say the eigenvalue of 0 is with multiplicity 2. Right. So, see, without looking at it, even if I look at the structure of this graph, I can say it immediately. If I have two parts, I know if these two are connected, completely they are connected, right. There is a complete, I mean all edges are possible between these two. That is what I mean by join, right. If I take the complement of it, obviously all these edges are not going to be there. That means what, I am going to partition my graph into two sets, G1 and G2, they form I mean they become disconnected in my complement, right. This is what structurally you should be feeling, and the same thing also you can realize it from your spectral values. Okay. So, this is something about the algebraic connectivity, right. So, yesterday we saw why algebraic connectivity was so important, right. Even in the evening's lecture we saw we have to worry about this quantity, right, because we in many cases we want to get this in an optimal position, right. We want it to be maximum in some sense. Right. So, what does this value reveal to us? What does the algebraic connectivity as a value, what does it reveal to us? So, of all the classes that we have seen, what is the range for this we have seen, right, not largest. So, second smallest, we are talking about lambda n minus 1 of the spectrum, in the spectrum of L of G, we are looking into the second smallest. So, we know one thing, if lambda n minus 1 is equal to 0, I know my graph is disconnected. So, this is not at all going to give me a good feel. So, let us not worry about this 0 eigenvalue. What if my lambda n minus 1 is positive? So, in connected cases, how big it could be or how far can it be from 0? So, what are the collections that we have seen already? At least one class we have seen immediately, you can say what is the value of lambda n minus 1 for k n? So, like let me just rewrite this instead of AC. So, let me call algebraic connectivity as AC of G. So, for complete graph, what is the second smallest eigenvalue, guys? There are only 2 eigenvalues for that, you cannot think so much. Yeah, n, right? So, if I look at Kn, it is n. So, what about Kn minus an edge? This also we have seen, even in the morning we saw n minus 1, n minus 2, n minus 3, n minus 2, right? There are only 3 eigenvalues if you delete an edge, 0, n minus 2 or n, right. So, we can see that if for any non-complete graph your algebraic connectivity reduces to n minus 2 or maximum is going to be this, right. So, n is a very special case, you get only for complete graph. Your algebraic connectivity is equal to n only for complete graph and not for any other collection. So, the next question comes, of all connected graphs on n vertices, what is the algebraic connectivity or how small can it go or how large? We know how large it can go up to n also, right, and we know that in general if my G is not a complete graph, connected and not complete, then this would be less than or equal to n minus 2, right. So, the next question is, of all graphs on n vertices. So, now we are focusing only on n vertex graph, right. So, there is a range of possibility for the collection, for this collection. So, in this collection, how small can my algebraic connectivity be? Of course, it is not 0, we are again of all connected graphs, we will worry about only connected, because again you will say 0, because for disconnected we have 0, forget about that. So, for all connected graphs, of all the connected graphs, how small can my value go? Okay, n minus 2 I can see if it is not complete, but how small or how close could it come to 0? Will it come close to 0 or where can I expect this range to be, and which class is going to satisfy this, or which graph is going to satisfy that small value? Is it a class or is it just a single graph which would satisfy, like Kn, it is a single graph, it has a different property, right. So, these kind of questions is what we usually ask when we study spectral, and we try to design the structure, right. We have to decide about the structure of the graph from the spectral values. So, answering such questions will give us the lead. So, what do you expect? Which graph should be having least algebraic connectivity? Intuitively, if you would have done the exercise that I gave you, you would have given me the answer immediately. I asked you for the Laplacian spectrum of cycles and paths, right, Cn and Pn. So, Pn is considered to be having the least algebraic connectivity, okay, a path on n vertices. Pn is going to satisfy this, and how small this value could go? The value is somewhere typically in this range, 1 minus cos of pi over n, yes. Okay. So, it is less than 2 provided this value does not vanish. So, you have to look into the spectrum of Pn and spectrum of Cn. If you see, they are somewhere closer to this, okay. Cycles and paths, they are closer, but even among that the paths, they give you the least algebraic connectivity. So, now what can we say about the algebraic connectivity of a graph G? Okay, given a algebraic connectivity of a graph G, what can I say about a graph G1, where G1 is nothing but G minus V1, V2, Vk, some k vertices, I will just remove it, okay. So, next we have to look into other possibilities. If suppose I have a graph G, and if I want to delete a vertex out of it. So, this comes into the study when we do dynamic graphs. You keep adding and removing vertices or edges into the graph. How will my spectrum changes? What is the dynamism of my network? How does it impact my spectrum of the graph? Okay. So, can you think of this? How much will my algebraic connectivity vary, or it does not have any impact on that? Something should be coming out of this, right? Of course, when I say I am deleting a vertex, okay, let me just start from even, I do not want to do this big one, let us just remove one vertex and all the edges. When I say I am removing a vertex, I am removing all the incident edges on that vertex also, right. If suppose G1 is this, by removing one vertex out of this graph, what can I say about any relation between the algebraic connectivity? How are these two going to be related? Will it reduce from G? Because I know AC of G, right. Given G, I am trying to say I will remove one vertex out of it. If I remove that one vertex, what is happening to my network? How much my algebraic connectivity is affected by this, by removal of this particular node. This will give you the impact of the behavior of this node in the network, right. Because if I remove this, my algebraic connectivity either completely reduces, it goes to 0. If suppose I remove a cut vertex, right, my graph is going to become disconnected completely, right. So, that means what, this particular vertex has a crucial role over there, right. So, how much impact is going to be taken there when I delete that vertex? So, this is what we need to look into, right. This is a very important question when we try to study network properties, especially dynamic networks. When we go into dynamic networks, these kind of questions will pop up. Okay, this is given to us. I want to ask the question, how is my AC of G1 and AC of G related? So, I am just asking is relation, just a general relation. Intuitively, what do you feel? Will it reduce, increase? Yes? Less than or equal to. Okay. Then my next question will be it be equal to? When will it be still, I mean it is not at all disturbed? Will there be a possibility that it is going to be equal? If so, when? So, what he says is, if suppose from my G I remove the vertex which is isolated, then what happens to my algebraic connectivity of this graph G1 after removing one isolated vertex? What will happen to this? What if there was only one isolated vertex in my graph? Yes, it will increase, right, because my G1 might now become connected after removal of this isolated vertex, right. So, in that case my algebraic connectivity increases. So, now we have got a counter to say that AC of G1 can be greater than AC of G. So, this part we will keep it aside. What if my G was connected, that is there is no degree 0 vertex at all, then if I remove that vertex, what will happen? So, coming back to this question, so if G is connected, then what happens to my G1? So, one answer was it reduces. So, obviously it reduces, okay, the connectivity is reduced by deleting one vertex, but how far will it reduce, or will it be equal? When we say less than or equal to, then we should also look at the possibility when it would be equal, right, when the algebraic connectivity is not affected by removing a vertex. So, we can get a feel that if I remove a vertex, connectivity is somewhere disturbed, right, my somewhere there is a disturbance that is happening, but for how far, if you see, it is not just less than or equal to, it is going to be less than or equal to AC of G minus 1. If I remove one vertex out of the graph, I can say that it reduces by at least 1. Okay. If I remove say k vertices, then my algebraic connectivity will reduce by k from the original graph. So, I will give a proof of this if you want in the next class, but think about such questions. Okay. What will happen to algebraic connectivity of graphs if you are doing a join, right? Say two graphs are there and you are doing a join, already we know certain things what is happening. Suppose you are looking at disjoint union, then how the impact is going to be there, right? Like sum, join, union, all these are basic operations. With respect to this, how will my algebraic connectivity be altered? Okay. These are one direction to see, and then we will look into, in the next class we will look into algebraic connectivity of trees. Okay. Trees also have a very different role to play, for which we have not studied any of these properties, right. So, we will see about Laplacian spectrum, adjacency spectrum of trees, okay, and also other classes of matrices.